Thank you very much. Would you turn to your day 3 notes on torque? We're just going to review. There are some few things that you're going to add as a review because they are additional. The first thing we started with, and before this mod, was translational. So you have a note on that from last mod. That's when we moved straight across from A to B. Now, we had two kinds of translational movement. Do you remember what that was? One was when you were still, and one was when you were moving at a constant velocity. So we had names for that. Emily, one?
Was it static and dynamic?
Yeah, static is when it's still, dynamic is moving but with no acceleration. All right, so we switched from translational land to rotational yesterday. And guess what? I failed to tell you. There's two kinds. Guess what they're called? Static.
And dynamic?
Yep.
Oh my goodness.
Alright, so static means
Like
you have the ability to go in a circle. You're set up to go in a circle, but you're not going in a circle. So you're still. Dynamic means you are moving in a circle, but at a constant velocity. So no acceleration. Just like in translational. So they're very similar definitions and easily relatable. Then we went on and we looked at a situation where we had a spot. Do you recall what the spot was called? Zach, what was the name of the spot?
It's like the rotational axis.
The rotational axis. Fancy name for a spot. Rotational axis. And from that, we established an imaginary line, which in this case actually is provided for by the handle of the wrench. So do you recall the name of that, Alex?
The lever arm.
Right. And we had to have a force, and the force was perpendicular. And I had a question for you. Again, I didn't address everything yesterday. What if the force went this way instead of perpendicular? What do you think we would do with such a situation? Having seen similar situations all year long, what do we always end up doing with diagonal forces?
Finding the vertical and
Right.
horizontal.
Right, so if our force went in that direction at a given angle, we would have to come up with dividing that into two. So we would go like this and any other color like this. So which of those, the orange or the yellow, would count in this?
Yellow.
Right, so only the part that's perpendicular. So we won't have those problems for a while. But what's a little sine and cosine? Among friends, we can handle it. But for now, we're going to have our forces perpendicular. But I just set you up for observing that later. So torque had a formula, and it went like this. The sum torque equals, well, we'll get to the sum of them in a second. So do you recall, Brian, what are the two things that we multiplied together to get torque from yesterday?
Force units and the
Yeah, it
units
was-
of distance.
All right,
So
all right, so we meant
newtons
force, you said force, perpendicular always, and
and
distance.
the radius.
All right, and what units will come up?
Newtons. And,
That's for the force.
and meters.
Right, Newton meters. And we do not rename that. We actually use Newton meters or foot pounds or similar units. So Newton's second law comes around and says the sum of the torques equals MA, just like the sum of the forces equals MA. And we ended yesterday on a seesaw, where wherever there's a force that causes rotational movement, we notice that actually it is rotational from a seesaw. What do we call this spot right here? Do you recall, Emily 3?
The fulcrum.
Fulcrum. So fulcrum is like the axis of rotation. It's usually called that when you have something like a seesaw or a bar or a rod or something that's balancing on a point. We usually call it a fulcrum, but it still has an axis of rotation right there. So we notice that when somebody has a force from their weight, and it's on a seesaw, it does cause rotational movement. Which way do we decide to be positive and which way do we decide to be negative? Emily, one?
Clockwise is positive.
Right,
and counterclockwise.
right. And I think that pretty much brought us up to the point
Wait, you
where
want, it's the other way around. Like backwards.
oh, this is clockwise? No, you're right, this is clockwise. You said it right, I wrote it incorrectly. All right, so a clock goes this way. All right, I got it. All right, so with that, we are going to actually do problems. So we found yesterday that each of the weights will cause a torque. So we're given the weight and we're given the distance, and if it's in equilibrium, which the problem is, the sum of the torques would be 0. So that's how we did those problems. Let's do number 2 together, and then I'll release you to work on this sheet. I've got problems. Now you have problems. All right, let's look at number 2 first. I think you can do one
Yeah, one.
without any help from me. So would you read number 2, Alex, to us? And would you show number 2 to our fans in video land?
Fan club.
Hi people in Videoland.
All right,
That's one.
Alex, read number 2.
This is
Alright, 2 children play on a seesaw. One weighs 221 newtons and sits 1.12 meters away from the seesaw's fulcrum. The other weighs 171 newtons. How far from the fulcrum must she sit in order to balance the seesaw?
All right. So if you would sketch in, first put some faces. They look kind of like zombies. So go ahead. After that, would you put in
See their
a
noses.
arrow indicating the torques that both of these
Now they look really
people are
creepy.
going to cause? So we have basically
It definitely looks worse. I'm not from face
a female here, a male here, and this is 171. The force perpendicular is 171 from the female, and it
There you go.
is 221
No,
newtons from the male. So we also know one more piece of information, and that the male is 1.12 meters away from the fulcrum. And they want to know where they want it in equilibrium, they want it balanced. So where should she sit? How far from the fulcrum? So first of all, sketch in a picture of the torque that this one causes. So imagine there's no one on this seesaw. Would not her weight cause a torque this way? And the other one will go this way. So we decided that this one is positive and this one is negative. Do I have it right?
No.
Clockwise is
positive.
1.12 times 2.1.
Alright, I look at the clock and I still put it up incorrectly. Alright, the clock goes this way. I can do this. So this is positive. The clock does not go this way. Except in some really weird movies. Some weird movies it might. But, what's that?
Well, the clock is kind of the odd circle out.
Yeah,
I mean, it's like one of the
You're
few
right on
things
that.
that will actually match what's supposed to go.
that's true.
Just so I remember how to do it later.
I've been looking at too many digital
Done like
clocks,
the
I
first
can't
one.
do clockwise anymore. So, alright. Just help me when I have those points. So, they're saying that it's balanced, so the sum of the torques equals 0. There's 2 torques. I drew one in orange and the other in orange. So I'll start with the negative one. So torque is going to be force. Remember, weight is a force. Force times distance. We don't know this distance, so I call it D. You call it X, whatever your variable favor is at this moment. So minus, then we have a positive torque. Remember, the formula says to add up all the torques, so we're on the left side. And we have 221. Remember, weight is a force, so force and distance is 1.12. And what will it equal? What's MA going to be in this case? 0, because we're balanced. There's no acceleration. The problem stated that. So we just solved that for D. Calculator, tippy tap.
Alright, this next one.
Experiment bars balanced on full.
So it's just gonna be 3.0 kilograms.
The distance is, X is, whatever your variable.
We don't
Share it
put
with me.
meters.
Yeah.
Looks like we're,
Wait.
Point,
We also change this to newtons.
go ahead.
negative 1.4.
And this is 1.4.
Doesn't it change to?
Alright,
Yeah,
when,
it's
Oh,
1.4.
This has to
yeah,
be
because we have a
meters, so-
negative, either move that over and divide, or move that
Or
over
just
and you
make
have a
it 1
negative
into
divided
meters.
by negative. So either way, you get a positive. And what's the third digit? I see I've got 3 digits everywhere.
4.
1.44,
Wait. Oh yeah, it is because kilograms.
is that confirmed? 1.44 or 1.45, which is it?
I got 1.4.
Actually, technically, it would be 4.5 because it's 1.447.
Okay, yeah, we'll have to go up then. And that is meters. That's where she needs to sit. That's how far from
we
the
have to put the
fulcrum
45
she
into
needs to
meters,
sit
though?
to completely balance the system.
So
0.45.
Alright, do you see how the problem number
Yeah.
3 will work the same? It's not a seesaw, and you will change the kilograms to weight before you can proceed. Alright. Yeah, you can do number 1 now. I think you're pretty good at number 1, but read it through. If you need direction, I'm here. Alright. Hunter, Brandon, we're gonna shut down the video while we work on this worksheet. Have you shown them the whole thing yet?
no.
I'm gonna give you a blank one if you've already written on it. That's good enough. Alright, show them all the problems. If you haven't gotten that yet, you can pause the video and work on them on your own paper.
It's the second page. Woo! Exciting. Look at that.
Picture.
So much fun. You guys are gonna love it. Alrighty.
Bye.